Next, I'm very happy to announce the SIGCOMM Lifetime Achievement Award goes to Professor K.K. Ramakrishnan for his pioneering, sustained contributions in the research, design, and standardization of network congestion control and avoidance protocols, virtual private networks, operating system support for networking, and carrier-grade voice over IP. KK is a distinguished professor at the University of California, Riverside. Previously, he served as a distinguished member of technical staff and a founding member of AT&T Labs Research. He previously served as technical director at Digital Equipment Corporation and was founder and vice president of Terra Optic Networks, Incorporated. It would be no exaggeration to say that KK is father of congestion control. His work on DECBIT paved the way for router-based congestion control mechanisms in what later became seminal works on data center networking and wide area congestion control algorithms. In RFC 3168, he made the initial protocol of ECN, the proposal of ECN to the IP protocol, which is now supported by most major operating system vendors, as well as influence transport protocols such as QUIC. And these are just examples. His contribution goes far beyond that. In my opinion, KK's success derives from his ability to create technologies that are extremely innovative, but are also correct by design, allowing them to withstand the test of time and form powerful building blocks that all researchers in our community can build upon. So few have had such major impact in our field, and so he is truly deserving of this award. And we are also very lucky to have him here today, and he's going to give a keynote talk. So thank you, KK.
Thank you all very much. I'm really, really honored to receive this award. And when Renata sent me the email, I thought she was joking. So I'm going to try and talk about something that maybe is at the top of my mind right now. I was actually debating on what to talk. There isn't very much I know that you all already don't know. And like my students always say, anything that I talk is pretty boring, so I'm going to try and do my best at being as boring as I can. So I talked to a few people and they said, well, it's not such a big deal. You shouldn't be thanking all these people, but for me, this is a big deal for a little guy. You don't get that many occasions. And in my mind, so many people have helped me along the way. Understanding, most importantly, dealing with life, how to be a good, honest person, understand technology. And, you know, a lot of people have sacrificed. I think if you go from one of these countries like India and China and so on, and you go to the US, you sort of abandon your family. You do your best to make up for it, but there's so much that they sacrifice, my parents, my siblings, and when you move to the US, you're a very small insular family, and my wife and son have put up with me for all these years, and I have to thank all of them and my relatives as well. And especially teaching me over the years and my advisors. I was very, very lucky going to digital equipment, and we started in a research lab that promptly got killed. And I got moved to a networking organization that was run by Tony Locke, and I was very, very fortunate to be in that group with people like Tony and Bill Haw and Joel Emmer and Henry Yang and Raj Jain, who helped me along the way. And when DEC started going down, just like many other places that I've had the good fortune of being in, I ended up going to AT&T Bell Labs, which I looked for stability, and about a year later they said, well, they're going to break it up. And I was very, very fortunate to have Sandy Fraser guide me. And one of the things that he told me was, well, you're just as good as everyone else, but you don't know how to articulate, and that's how I've been all along. But that's helped me along the way a lot. And Chuck Kalmanek, who was our VP of Research, really supported me throughout. I learned a lot from one group, especially the end-to-end research group, and I've collaborated with a huge number of people, and I have to especially thank people who I learned from, like Dave Clark, and a really, really good friend and supporter, Sally Floyd, and many others, some of who are here. I spent a lot of time working in networking standards bodies to see how they strived so hard to make things as complicated as possible. OSI, ATM, and so many others that helped me to learn about all the potholes that you can go through and dead ends. And I really learned a lot from going through all of that. I want to thank Renata and the SIGCOMM Awards Committee for picking me. I think there were many, many other deserving candidates. Ken said, you must remember to say, well, there are a number of people I'm sure you would like to thank, and I believe I should, but those are people that I'll have to take another time to gratefully acknowledge their help. So let me talk a little bit about a couple of efforts that I've been working on to try and bring together some of the things that I've learned in the recent past. And I thought I'll start with talking about how I started working on congestion control and go back through history, but that would be even more boring for me than it would be for you folks. So I'm going to try and talk a little bit about the things that I've been working on more recently, and try to draw some learning out of that, especially with the growth of data centers and cloud computing. I see that, especially for somebody who's come from working in traditional networking, data centers in the early 2000s seem like a little bit of a novelty, but they have really, really changed how we use computing. And compared to what it was when I started, they've really also been enabled by the widespread availability of networking. So I wanted to look at how cloud computing and data centers have changed how we think about networks, especially about how much functionality that is typically network resident has moved into the cloud, and how that influences how networks work as well. So I'm going to look at two topics. One, cellular networks, which I know is not an area of that great interest to a lot of people, but it is something that does influence so much of what we do in our life in any case. And the other area that is of interest to me now is serverless computing, to look at how we can take some learning about how computing and networking should work together. Before I start, I wanted to make this observation about how software gets developed, especially for cloud-based applications, where we build everything using these microservices. And it's wonderful because you are able to independently develop and deploy, and helps from the point of view of scaling and so on. And it's an approach that has become really popular even for how software-based networking applications are built. And if you look at many of the large information providers, they build so much of their applications using these microservices. And I want to take some learning on how we could look at networking a little bit of a fresh eye in that context. And one of the things that I started my main work on software-based networking was to start looking at, I had some notes for me there, I should have removed, but I started looking at network function virtualization, and a comment that was made yesterday was, oh, you must have a lot of guts to come here and talk about NFV at this time in this audience. So I know it's not something that is in, but it's something that we use so much of. And networks themselves have moved so much to a software base, driven by so many factors. First being system capabilities, and how OS has evolved as well. And so much of network functions run in software now, and they're all built using the same microservice architecture. And the one area that has helped us a lot for that is virtualization and support provided by DPDK. And we built a network function virtualization platform called OpenNetVM that's built around a shared memory framework. And that helped me to learn a lot about how to use OS and networking sensibly. What we did was basically to run these functions inside containers, and we put a lot of effort into not doing data movement, getting rid of interrupts, being careful about how to avoid locking, and to help scale. And we got pretty good performance even in those days, about 10 years ago. And that helped me to then go off and look at how to think about these capabilities being introduced into the cellular network. So if you look at the cellular network, we end up having base stations that provide the air interface to mobile devices that then the data gets backhauled to a set of components that now are evolving to primarily being software. They've evolved from what was purpose-built hardware appliances to this virtualized software-based infrastructure. And that's this core network. And it's really composed of a number of software-based functions. And if you look at how that cellular core is built, it's basically a bunch of control and data plane components. The control plane functions communicate over HTTP REST interface, and you end up then having a interaction between the control plane and the data plane, all in a co-resident software infrastructure. What used to be otherwise many, many hardware components. So the stress on the packet core is really that going beyond what people have been doing on the air interface is to see how we can bring down latency and have a lot of flexibility in how packets are handled with this cellular core. And that's what I want to look into, how people have been building that. And we've also done a fair amount of work. There are a number of other open source efforts as well. And if you look at what industry is doing, whether it is Ericsson or Nokia or others, they're all following a similar pattern, which is to see how to build these components that are disaggregated in software and put it together so that we can really have a high performance control plane. And this control, the cellular core is really a pretty key component because if you look at mobility, you need an anchor point, and that cellular core ends up being the anchor point, and you have that influencing a number of things that we do, whether it is for session establishment, mobility, policy, and so on. And the thing that we see is that there is a very tight dependency between the control and data plane, because before endpoint exchanges data packets, a whole bunch of control messages have to be processed by this cellular core to set up that data path and to turn it on and off when a end device transitions from one state to another. And the core ends up playing a much, much more significant role as cellular networks have evolved, especially when you look at using higher speed links. You have to move to smaller and smaller cells, and that means you end up having much more frequent handovers. And if you look at how we're using cellular now for ubiquitous connectivity in a disconnected world, then you end up seeing that there's more and more control operations, like for instance with IoT and so on, that you have to deal with. So we have been working on how to build a more performant cellular core, but from there we also took some learning on what is really needed to go beyond just looking at a better implementation. And one of the challenges that we had was looking at this service-based interface, which is using HTTP REST APIs for the control plane. The penalty that we saw, and I'll go into a little bit more detail later on, is that with that interface, with using networking in this very convenient general purpose interface with REST, is that you end up having a lot of the typical networking overhead that we see otherwise, with movement of data, serialization and deserialization and so on. And that contributes a lot to the control plane latency. And if you look at a bunch of papers in the recent past, we've seen many, many efforts to try to improve that with having different approaches to minimize some of that overhead. And the other thing that we see is that, and I'll show you a little bit of how complex it is. If you want to hand over from one base station to another, you end up having a fairly complex handover procedure. And a big part of that is that you have data that gets forwarded from this anchor point to where the mobile device might have been before. And then when it moves over, you have to move the data, and that data is moved through the cellular core again. And so you end up having this triangle routing and overall the hairpin routing, and overall it ends up having a significant impact on the user experience whenever you see a handover. So what we end up needing is this control plane also, not just the data plane, to speed up, and we need efficiency improvements there as well. And that's what we've focused on and what we've implemented with this NFV architecture that we use. So the one key point that we observed is that a number of these software functions that are communicating with each other are using what is a REST API that was meant for client to a server communication. And instead, what you have is a number of software components, microservices, that are co-resident and unnecessarily going through a substantial amount of overhead for communicating with each other. And so we looked at how to use simple shared memory across these virtualized components for communication and built a platform that has much, much higher performance by saying, well, I don't need to move data at all. So data is accessed in place, and there's no kernel overhead involved, no protocol processing involved, and you just don't have to have data moved across these functions. And that brings down the control plane latency substantially. Of course, you have a single node that has these components. The reason that we disaggregated them is because you want to scale them independently. So in that sense, when you want to scale, you have to have a sensible method of scaling them up. And for that, we said, let's start thinking about having these as a unit and replicate them. But then you also want to be able to make sure that the number of components can actually sustain a very large number of mobile devices. So you might have to have a state-aware or a endpoint-aware load balancer, and also look at how, in some cases, go across nodes. So we've been looking at using RDMA for that. So if you look at this service-based interface and you say, well, I'm just looking to avoid some of these overheads that are involved for moving data from one network function to another, the traditional way using JSON, it's very convenient, but really it's a killer. It takes you a millisecond to move a message back and forth between these functions, which is tremendously wasteful. And when we look at using shared memory, it completely eliminates all of that access cost. And if you look overall, taking a pure kernel-based implementation and an implementation that is based on a more sensible way of sharing data across these network functions, you bring down the completion time for these control operations by a factor of 2. For instance, when you think about a mobile device that saves battery power and turns its radio off and then has to be woken up when you get a packet to be delivered to it, then you see that you have hundreds of milliseconds to go through the process of waking up a mobile device before you deliver data. And that is something that you'd really like to reduce, because the amount of investment that is going into the radio part of the cellular network is substantial to cut down latency, but then we eat all of that up in having a very inefficient general purpose way of communicating between these functions in the control plane. So we said that helps a fair amount, because you do see a reduction in the control plane latency that has a meaningful benefit from the point of view of a user experience. But still, this anchor point is really involved in so many critical functions. As I said, with saving energy on the mobile device, you go through this paging to wake up the device and deliver data, and the penalty that you pay for that. And when you go from one base station to another, all of these involve the need for changing both the control plane state as well as the data plane fairly quickly, so that you can also forward packets without delay. And the problem is that there are still so many protocol message exchanges that are involved in changing that data plane to go from one, let's say, from one base station to another. And if you look at mobility, when you're doing a handover, you end up exchanging about 25 messages back and forth among all these different components. And data that is coming to an end device has to be buffered until that handover is complete. So when we go through and improve this implementation, we do reduce that latency by a factor of 2, which is helpful. But what we see is that the complexity still remains because all of those messages get exchanged unnecessarily between all these different software components that are built as microservices. The problem there is that the protocol, which was built probably a couple of decades ago when we had all these hardware appliances, that protocol is so complex. I had a figure that really actually described the full protocol. It couldn't fit, obviously, and I couldn't read any of the words when I tried to fit it in. So I abstracted it out, but there's so many messages that are exchanged. And all because we continue to think in the same way as we did before when they were all distinct hardware appliances. Even if you just think about waking up an end device, I tried to do this a little bit better, where I said I'll look at those 15 messages that are exchanged between these different components. And those 15 messages are exchanged between these different components. Most of them are all resident on the same core network, a bunch of software components, other than the two that you see, the blue and the red, which is the end device and the base station. Everything else is co-resident on the same node. And again, you end up having to hold on to the packet while these 15 messages get exchanged, several tens of milliseconds for each one of them. So we said, look, a better system implementation helps, but it just really doesn't take full advantage of what you can if you were to say, let's rethink how we build these protocols when we move from a hardware base to a software base. And these existing protocols that are so heavyweight end up being harder than hardware in terms of changing. And if you try talking to some of the service providers or the vendors to say, let's rethink how this can be done, it's really hard because it seems like it's swimming up a waterfall. And that's really necessary before we get to a point where we can actually meaningfully use this for a number of low latency applications. And so when you look at having a software-based implementation, if you properly structure it, then that protocol can be substantially simplified. And just a couple of us thinking through this as carefully as we could through all these protocol exchanges that we saw with 3GPP. It took a bit of an effort understanding that protocol and then seeing what can be meaningfully done. We can easily cut it down by a half for each of those processes that I talked about before. So there's a number of things that you can do. You can restructure the way these messages are exchanged. You can do away with a lot of the messages. You can reorder messages. And most importantly, you have state that is available in memory that you can just use as is. And there's no need to even have messages exchanged between these components. And that all helps us in being able to move from where we had a simple, straight implementation of an existing protocol to something where we think holistically about the protocol and the implementation together to see how we can move things forward. And I see that as a pattern that seems to repeat, where we look from an expediency standpoint to say, let's use general purpose structures that are nicely abstracted, and then use them in an implementation. And you get some benefit if you try to structure the implementation carefully, but you really don't get the full benefit of really considering refactoring both the components in the network, how they get implemented, as well as the protocols together. And so, I realize cellular networks, small group of people, increasingly smaller group, increasingly companies that are losing money are working in that space, so it may not be as interesting. But let's look at another, which is how we do networks in the cloud, especially from a standpoint of making the cloud be more accessible to users. And I want to look at how we use network primitives in that context. And the area that some of my students and I have been working on is looking at serverless computing. And that's one of the faster growing offerings. Even if you were to think about how we use serverless computing in the space that all of you younger folks are working on in ML and so on, serverless ends up being a very convenient paradigm to use there as well, where you're basically using this function as a service where users are focused primarily on developing their application and letting the cloud service provider take responsibility for everything else, including making sure that they scale the service properly and to have the appropriate management structures for having the code resident. So the characteristic of these serverless functions is what one would expect, that they're short running, they're stateless, and they're event driven, and it helps from the point of view of the user in that cost and complexity is completely or reduced considerably, and you really don't have any always-on server components that are running. And the cloud provider is taking the responsibility of provisioning, managing the infrastructure in its entirety. So the event-driven execution is something that is really attractive. And what the cloud service provider takes responsibility is to say, well, I'll start it up just in time. I'll make sure it's terminated on completion. The more sensibly I can do that, the more revenue I can generate by having more functions served on my infrastructure. And from the user standpoint, it does reduce cost. So if you look at microservices that are built, applications built using microservices, now you can have them run on a serverless cloud. And if I look at the infrastructure that a cloud service provider needs to provide for that serverless cloud, what you see, and I'm using the example of Knative, which is what we've been working with quite a bit because it's open source, but it is representative of a number of other serverless environments, whether it's open source or otherwise. And what you end up having is requests showing up at an ingress gateway where you basically do authorization, authentication, and so on, and then pass it on to having that request served, essentially through a message broker that is responsible for doing interfunction networking. And then the core task is done by these user containers or function pods, which basically have a couple of components. One is a user container, and then another that is critical for handling the requests that come in to a function container, which is a sidecar. And that sidecar is involved in making sure that the function is running, holding on to the request till that function is up and running, making sure it's healthy, collecting metrics and so on, and then using that metrics that are collected to hand over to an autoscaler and a placement engine and so on to do the things that are needed in the control plane to get the system up and running. So I said this looks awfully complicated, and when I look at the performance of something like this, when I started, I was shocked at how wonderful the performance was, meaning how terrible it was. And so I asked my students to go off and do a little bit of careful understanding of where all the overheads are. And so we did a little bit of careful auditing, and this looks a little painful, so I'm going to walk through this just a little bit to help you understand or help me explain what's going on. So you have a request that shows up, and it has to go through the kernel protocol stack, and then goes into a virtual Ethernet interface, and from there on to get to the ingress gateway. And the work that is involved to deliver it up to that ingress gateway involves interrupts, protocol processing, data movement, deserialization before that ingress gateway says, okay, now I have the request that I can then hand off to a message broker to say, well, hand it to the right appropriate functions in my infrastructure. So that request goes through a bunch of overhead. That's what one would expect normally when you're dealing with a HTTP request. But when you then hand it to this message broker, you go through all that overhead again. Why? Because we're using general purpose interfaces and use them to build these capabilities as rapidly as we can. And so you go through all those overheads one more time, as if you're coming from the network to that message broker. And then from there, you decide, well, I'm going to send it to the appropriate function, which is this container, that or pod that has the user container and the sidecar to deal with it. And so that request has to again be processed. It gets delivered to a sidecar, which is a proxy, go through all of that overhead again, and then from that sidecar, go back through the kernel protocol stack up to the user container again. So huge amounts of overhead there before you say, I'm now going to execute for this few hundred microseconds or a millisecond that small piece of code that is running in that microservice that my user provided as a function. And then from there, I have to get it to the next function that is part of my microservice. How do I do that? I have to get it back through my sidecar to the message broker, and from there, again to the next function. And so as I go through this whole process, if I just do a simple accounting of all of the overhead that's involved, it's such a large amount of normal network processing that we would do if we went from one node to another node to do all of this work. And the reason is that we tend to do all of this to maintain generality and to be able to bring these things up quickly. And if I were to say, well, production platforms do better, probably. Oh, I'm going backwards, sorry. But when I look at the performance that you get out of these production platforms, they're not that different. There's still inherently a fair amount of overhead, even if it's a closed source environment. So we said, how can we get rid of some of these overheads? One is, if you look at this container-based sidecar, it's very convenient as a proxy to do a lot of the work for the function container, but they're stateful, constantly running, and if you look at having another proxy that is handling forwarding between functions, this message broker, that's also constantly running. And all of these unnecessarily consume so much resources. And you have to go through the traditional networking to get from one component to another. We said, can we get rid of a lot of this? And a couple of years ago, 3 years ago, we discovered what you all have discovered quite a while before, about how this whole notion of eBPF can be used in this context effectively. So it's really helpful to use this for event-driven interaction. And what we see here is that if we were to look at this function, the sidecar container, that is something that is eminently suitable for using eBPF as a way of providing the event-driven functionality that is needed, that otherwise is handled by this proxy that is constantly running. And the message broker is another one where you're basically just doing event-driven processing to forward the request from one function to another, and that's also something that can be easily replaced with a eBPF function. So a lot of the work that we see with functions that are running inside a serverless cloud can be replaced using eBPF. I probably shouldn't be covering this slide because most of you probably know more about this than I do. But what we're doing is basically taking some very simple C code, going through a verifier to make sure that it can safely run in the kernel, and then put it at the appropriate hook point in the kernel for being able to provide that event-driven capability that the user container needs. So that when you have an event, you can have that hook point invoked to execute the function that's needed. And the stateful work that we need to do for, let's say, handling metrics and so on, eBPF has this component called the eBPF map that is in the kernel that can be used to handle that state. And for routing, when you're going from one function to another, which is the key reason that we end up having a very heavyweight message broker, we can use the eBPF map for that. So this whole notion of using hook points in the kernel with eBPF helps us tremendously to take the programmability that it provides to be useful in this serverless environment. And all of the stateful processing that we need can be offloaded to the kernel so that we can still continue to maintain the stateless way that functions are handled in a serverless context. So we built this platform called Sprite that some of you must have seen before, where we replaced this individual constantly running sidecar with an eBPF-based sidecar, which is basically to have the appropriate functions running in the hook points associated with the individual functions. And then we basically used shared memory processing to completely eliminate data movement and use a eBPF handler to basically forward requests directly from one function to another. And that considerably simplifies interfunction invocations as well. So with that whole approach, what we end up seeing is that we completely, when you go from one function to another, at least within a function chain, we get rid of most of the overhead that's involved, whether it is in terms of data movement, protocol processing, serialization and deserialization, and so on within that chain. And using this eBPF-based event-driven capability and the shared memory work that we've been doing for such a long time brings a substantial reduction in all of the overhead that we have within this serverless function chain. And if you look at performance, we can get 5-6 times better throughput. And if you look at the thing that we care a lot about from a user experience standpoint, it's tail latency, and you can get an order of magnitude more. And compared to the baseline platform that we used, we can get 50 times better tail latency. And with a lot less, 10% of the CPU resources that are consumed for the same sort of work to be done. In fact, much more work to be done. So the takeaway that we had was, look, if you are building microservices, even within the cloud, you want to be able to use the right, appropriate functionality for communication inside the cloud. And this eBPF-based event-driven processing that we had helps reduce all this long-running stateful components that are running in user space. And the shared memory processing helps us tremendously once again. And so that helped us to make the serverless really, truly event-driven and load proportional. So from these, what I saw was that as networks change to go to a more software-based environment, we need both, one, to have the protocols understand how you can exploit that software-based environment. And cellular example is an eminently suitable one because of the complexity that we see in the protocols that the cellular network uses. And we really need to take the opportunity to rethink protocols that we use, not just implement the same set of protocols in those types of situations. And when I look at applications that run in the cloud that use networking extensively, especially because of this really convenient paradigm of microservices, then we really need to also rethink about how we use network primitives and what are the primitives that you want to use to get good performance. And I found that eBPF was a really useful tool along with shared memory to help achieve this whole event-driven capability. That's all I have. Thank you, folks, for listening. I think I didn't run over time.
Oh, no, you're great.
Okay.
You can stay here. We can take some questions.
I would prefer to escape, but yes.
Yeah, so we have time for questions now. If you could, there's 2 microphones here and here. We also have some volunteers with mics who can run around and talk to you as well. So you can kind of stand up and or raise your hand if there's any questions.
No, there aren't.
I'll ask a question while you guys are thinking. I know that there's been some proposals for programmability in cellular networks, things like P4 and SDN. I was wondering if you had any thoughts on how that would affect kind of some of these complexities of kind of messages going back and forth. Do you think programmability could help or hurt?
Certainly, people have been looking at using P4 but looking at how to use the switch programmability to adapt to the current way that that protocol has been constructed. Okay, and they look to say, well, I'm going to use the switch primarily for what it's good at, which is the data plane, and to use the programmability to adapt that data plane as we do in any cellular network implementation, whether it is hardware appliances or the software-based framework, to have the control plane modify the data plane state to say go on and off, or forward it one way versus another for handling mobility and so on. So the P4 capability is used to adapt the data plane, but all of the protocol work that is done in the core 3GPP framework still remains as is. And that's where you really aren't going to get the benefit, except for the faster forwarding that you can with the switch.
That's great. Yeah, let's see, we can take questions. I see a question there, yes.
Hi, thanks KK for sharing your insights, very interesting. So you noted that the motivation for using the general purpose stack and general purpose RESTful implementation was ease of deployment and rapid deployment, and you sort of framed this as the cost, as the performance cost of that. So I wonder if you could turn it around now and say if you could say anything about the sort of cost in terms of programming and maintenance of going to this, to the new framework. And have you thought about maybe ways of automating that or something?
So there's so much work that's been done or being done for how to be able to automate some of the eBPF coding. So the things that I do agree that it does involve more maintenance, but if I look at some of the core primitives that we are thinking about here, we're still using the functionality that you want from a robust network protocol stack where it belongs. But where you say, I don't need the network protocol stack, you want to be able to use a reasonably well-structured library that provides the other capability for data sharing. We do so much of that in data centers with RDMA, for instance. DPDK is used by a lot of people for doing shared memory. You can use simple shared memory structures without a whole lot of code with eBPF. And my belief is that these libraries that you create are simple enough that you can maintain and evolve as needed.
Yeah, thank you. We can take a question. Yeah.
Yeah, can you hear me? Yeah.
Yeah.
Hi, KK, thank you for really nice and insightful talk. So I think the example you partially kind of illustrate some of the complexity and also part of the legacy, right? So if you look at the 3GPP, 5G core related kind of partially because a lot of protocol designed for hardware and appliances. When you have software, now things can be optimized. So one of the things which I kind of, your talk seemed to pointing that we need really kind of new type of abstraction to rethink about the protocol and the system design, given that there's a convergence of compute and communication. Have you had any thought, right? So for example, you're using eBPF as an example. Partially it's a new technology we developed actually fairly recently, and that can change some of the things. But on the other hand, I think some of the new abstraction may actually help kind of kind of provide impetus to even kind of new type of technology to kind of integrate performance, also reliability, and reduce complexity. Any thought on that?
Right. So if I look at how even protocol implementations of traditional networking, people are looking at how to use capabilities like eBPF to incorporate that code and make that much more programmable and flexible, right? And I suspect that that is very much appropriate even in this cellular implementation. The work that I did there was primarily focused on avoiding some of the traditional networking overheads for data movement and serialization and so on. I didn't end up focusing on looking at event-driven capability, but it is eminently suitable there and ought to be also incorporated and use that to then see how we can simplify. But, you know, there has to be some protocol specification that is still needed to drive and guide common implementations. eBPF gives you that programmability that you can modify locally in an implementation, but you have to interact appropriately with end devices that might be built by anybody and everybody, right? So those protocols still need to be there. But I agree that having a clear abstraction for what these interfaces can provide will help us to evolve the protocol from the very complex mess that it is in to being considerably simplified. I agree. Hey, Kun?
Yeah, it's Kun from Huawei. And Kiki, thanks for the talk and congratulations to your the award. Yes. So actually, I have a small comment, also a question for you. The first thing is that as you need for the service, and the needs is a characteristic of the function as a short running. I would rather say it is a capability, it's not the characteristic, right? So it means that for the service, we could run a function that's in short term. We can run short-term tasks. But nothing can prevent it from longer time.
Absolutely, and that is the thing that we tried to do with our whole design with event-driven capability, is that if once you stop having all of these heavyweight components running constantly, right, then the function can run for whatever time it needs to run, and you don't have to worry about trying to place restrictions and limits on how long it can run. And you don't have to worry about turning it off, turning it on, if you're not using resources when it goes off, right? So this making things truly event-driven helps us in completely avoiding all this cold start and placing limits on how long the function should run and so on. I completely agree.
So now the question is that, actually, you mentioned this two part. It's NFV in cellular network, and the service basically you say that for the cloud computing. But I see this similarity between them. Do you think that using the service technology to implement the cellular cores or the functions for maybe the future?
So that's what, when Zili said, hey, can I use event-driven capability? That absolutely, it's eminently suitable there for many of these components. Do I have to make those functions serverless? There are a number of these things that you can make them event-driven, but this notion of serverful, serverless, all of that sort of becomes fuzzy and not as important.
Yeah.
Thanks for the talk. I came up ready to ask a technical question, but I'm going to change direction completely given the audience. So when I reflect on your slides, I recognize that there are few people in our community, certainly not me, that have interacted with 3 or more standards bodies. And you look at the list with which you've engaged, they're very different governance structures, they have different means of reaching consensus. And so I wonder, if you could reach back and talk to yourself about why you decided to do it, any advice you might have when thinking about engaging with these groups to try and carry research out.
I
would you say to the younger
I
generation?
want to go to a standards body that gets locked in a room, and if they don't come to a consensus, they should be disbanded before they get out of the room. Then you'll see complexity dramatically reducing. I've been in standards bodies where you keep going on and on and on and on, and you think of how to make it more complicated so that it is more difficult for anybody else to get in. And I went to ATM forum and I said, look, you guys are trying to do something and IP is taking over, let's try to do something that's more sensible. And I worked on a signaling protocol. A lot of people liked it. First time I went and presented. By the time I showed up the second time to present it, they'd all thought like politicians of how to kill it, because it meant a threat to all the things that they're doing and to cut out all of the complexity that was already there. I think standards bodies are good. I mean, you need consensus to be able to have multiple components talk to each other. It's inevitable. You need protocols. You need to have protocols that are standardized. But we put, or at least I have not been going to standards bodies the last 10 years, because if you're an academic, you get no respect. Like, I feel very much like Rodney Dangerfield. So that's because simple ideas have no place, right? But standards bodies need a mandate to make things simpler, not to make sure that the standards body continues to survive.
Great talk. Thanks, KK, and congratulations. My name is Ying Zhang. I'm from Meta. So my question is, I really like your takeaway of rethinking the protocol, given the software, the new kind of software implementation. But if we think about protocol, essentially it's about state exchange, right? Like telling the other side what's the current state, and then it's essentially designing a conversation. So I want to know about some of the principles or guidelines, the takeaways you have on protocol design, given whether it's a separate hardware boxes or we have a shared memory. What are the kind of system aspects that can affect the protocol design philosophy?
You should have asked me this question, and then I would have been able to spend 6 months thinking about it, so then I can come and give a talk here, Ying. There are so many more wiser people here who can think about what are the fundamental things to think about for protocol design. Let me dodge the question.
I follow this question because the simplicity is what everybody pursue. And one question here is, you have shared memory, but shared memory in the implementation and also from the system aspects causes additional problems like the access control and potentially privacy leakage to, I don't know how many instances are sharing this memory. Then you have all the authorization issues and the privacy and many other overhead issues here. So you kind of shift the overhead from the network, let's say data transfer. Now you have additional problem in the software shared memory among multiple entities. That is probably how the protocol and the system aspects can be working together better to, I think, following the colleague from Meta, I would, go ahead.
I do agree. I agree that there are a number of challenges that come up, and we've tried to deal with some of them in our designs. there's quite a bit of work that the processor vendors have also worked on to try to make sure that you have the right structures for isolation. And so we've exploited some of them in the work. I've not gone into that here. But, even when we started with our first NFV platform with OpenNet VM, we said, let's see how DPDK helps us provide some isolation. And there it was more isolation through obfuscation that helped us to make sure that using the appropriate descriptors, you could make sure that only the ones that have access to that descriptor can share the memory. But there are more primitives that processor vendors and system vendors have created, like MPK and so on, that we can use to provide isolation in a more formalized way and control not just even different entities accessing memory, but even when you're looking at event-driven component that is running in the context of that user space process, you can still make sure that it only has access to the appropriate structures and not others. So there are capabilities that we've explored and exploited, but I didn't talk about that here.
Thank you.
Okay, are there any other questions? Please feel free to approach the mic. Yeah.
Okay, thanks for the talk. So at the beginning of your talk, you said that you send thanks to the many potholes and the dead ends you encountered. So could you maybe share with us a couple of examples and what you learned from them? Thank you.
So I probably will offend a lot of people, but I seem to have a habit of doing that all the time. But, for me, ATM is one big example. I spent so many years, willingly or unwillingly, when you're in industry, sometimes you do things you could maybe avoid doing that, and you choose to do what you want in academics. That is the nice part about being in academia. Of course, you still have to worry about funding, but Darlene has been so nice to me. She gave me my start in my academic life by just giving me some funding from the beginning. And fortunately for me, I didn't have to worry about funding so much, but I can see how it is with some others. But in industry, you have to do it. That pothole that I talk about, or I think of it more as a dead end with ATM, that it died because of what I said in the previous question, that they strived too much to make sure that they added just enough complexity to make it hard for anybody to use it. Right? And so it just died because of the weight of all the paper. Right? And I think that was one of the main concerns, and there were so many things there that I learned from ATM about how to recognize complexity that was unnecessary, like making sure that you have this heavyweight virtual circuit that has to be set up completely to just exchange a packet, when you can do this with very little effort, even in that base infrastructure, to be able to do some connectionless message exchanges. In fact, when I started in 1983 at Digital, Bill Haw had a protocol called Trailblazer that essentially did that, to say that I would start by being able to do message exchanges, and then where necessary, I would then put in the state that was needed for some connection-oriented message exchange. When I started going to IETF as a standards participant, there were 40 people in the IETF meeting, entire IETF meeting. And we talked about how, at that time, there was a lot of energy behind ATM. So we were looking at what to do for connection-oriented IP, but based on this base need for having some notion of context. And, we've learned that a number of these QoS things that say we need context and state, it's all gone away because the fundamental premise that they had before was to say we need simple end devices, and the whole thing is flipped on its head, right? You have end devices that are much more capable than anything that you see in the network, right? And you have now the network being absorbed in the end devices. If you think about where the network is now, it's mostly in the data center. But my lessons have been mostly about what not to do. But at the same time, I look at even congestion control. I learned a lot from ABR, where I learned how hard it is to do rate management carefully. I can keep on going, but I've bored all of you enough.
Yeah. Thank you so much. Yeah, that's very helpful. Thank you.
KK, I just want to share bad news with you. Darling just retired from NSF, so you need to find a new founder.
It's time to pass the flashlight, even for me.
Okay, are there any other questions?
No.
Okay,
It's time for a break.
yeah, time for a break. Let's thank KK.
Thank you.